Hello, and welcome to our discussion of trigonometric polynomials and basic concepts of Fourier series. Here is our first definition. A trigonometric polynomial is a function of the form f of x equals a0 over 2 plus the sum from k equals 1 to n of ak times cosine of k pi x over p plus bk times sine of k pi x over p, where a0, a1 through an, and b1 through bn are complex numbers, and p is some number that is positive. Let's pick this definition apart a little bit. I've separated out this a0 over 2 coefficient or term for later convenience. It'll make a formula a lot nicer down the road. I have an a0 term or coefficient, but no b0 coefficient, because if I were to plug k equals 0 into sine, I would just get back 0. Sine of 0 equals 0. The function f is 2p periodic, and this is a pretty straightforward calculation. We'll do part of it. Say I plug x plus 2p into f, I want to get back f of x. So I'll do this just for one of the cosine terms. I'll calculate cosine of k pi times x plus 2p, all divided by p, equals cosine of k pi x plus 2p k pi all over p, equals cosine of k pi x over p plus 2p k pi over p, equals cosine of k pi x over p plus 2k pi, equals cosine of k pi x over p. And you would do the same for the n sine terms. So f of x plus 2p is equal to f of x. Finally, you'll notice that I've only used integers k equals 1 through n inside the sum. If I put some negative integers in there, well, cosine is even, so cosine of minus x is cosine of x, and sine is odd, so sine of minus x is minus sine of x. And so those negatives would just pull out of sine or stay within cosine and affect the ak or bk terms. So there's really no point in having negative values of k in this sum. So this f is a trig polynomial. It's our basic building block for Fourier series. And we saw in last week's last video that if we took the initial temperature distribution for a heat equation problem to look like just a finite sum of sines, then we could get a lot of work done and solve the problem very explicitly. And now I'm allowing not just sines, but also cosines in the expression. And in a week or so down the road, we'll return to differential equations and see once again how initial temperature distributions and representations of this form and beyond can be very helpful. There is another way to write a trigonometric polynomial in a complex form. So say I start out with the trig polynomial a0 over 2 plus sum from k equals 1 to n of ak cosine of k pi x over p plus bk of sine of k pi x over p. I claim that you can find, and indeed you will do this in the exercises for this week, coefficients c0, c1, c minus 1, all the way up through cn and c minus n, such that this trig polynomial can be written in the form sum from k equals minus n to n of ck times e to the ik pi x over p. And this so-called complex form of the trig polynomial, not necessarily because the ck's have to be strictly complex and not real, or because the ak's have to be real and not complex, or the bk's have to be real and not complex. We call this a complex form just because I'm using the complex exponential. And this will be just as valuable a way of writing trig polynomials as using sines and cosines. Now these coefficients, the ak's, the bk's, and the ck's, are all uniquely determined in the following sense. Say I start out with a function f on the interval minus p to p, and I know that f has the form f of x equals a0 over 2 plus the sum from k equals 1 to n of ak cosine of k pi x over p plus bk sine of k pi x over p. Then I have to have ak equals 1 over p, integral from minus p to p f of x cosine of k pi x over p, and bk equals 1 over p, integral from minus p to p of f of x sine of k pi x over p. No ifs, ands, or buts. If you have f in this form of the trig polynomial, then you know what AK and BK are. And in particular, you'll notice that even though I separated out that A0 coefficient, this formula for the AKs, I didn't put any restriction on what K is. That's the nice thing of writing A0 over 2 is you get a clean expression for AK. And similarly, if you start with a complex trig polynomial, g of x equals the sum from k equals minus n to n of ck times e to the k pi x over p, then you must have ck equals 1 over 2p, integral from minus p to p, g of x e to the minus ik pi x over p. And you will prove all of these things with my guidance in this week's exercises. You'll cook up the relation between the ak and bk coefficients and the ck's. You'll also see how these integral representations all fall out. Now let's move to the actual series in Fourier series. A trigonometric series is an expression of the form a0 over 2 plus the sum from k equals 1 to n of ak cosine of k pi x over p plus bk sine of k pi x over p. So what exactly does this expression mean? How should we interpret it in a rigorous and clear mathematical manner? Well, let's start with all the data inside the series. We know that the coefficients ak and bk are complex numbers. Maybe they're real, maybe they're purely imaginary, maybe they have real and imaginary parts. We know that p is greater than 0, and now we have a new parameter, the independent variable x, which we'll take to be a real number. So let's think about what series mean in general. If I have this symbol, sum from k equals 0 to infinity of wk, and I have a sequence wk in C, this symbol does double duty. First, I'll define a sequence of partial sums. Sn is the sum from k equals 0 to n of wk. I can always add finitely many real or complex numbers together. And then the sum from k equals 0 to infinity of wk is first of all a symbol that denotes the sequence of partial sums Sn. So this sequence of partial sums, the output or the terms of the sequence are just Sn, and sum from k equals 0 to infinity of wk just literally means sequence of partial sums Sn. But then maybe this sequence of partial sums converges to a number s in C. That is, the limit as n goes to infinity of Sn equals s. In that case, I also write s equals the sum from k equals 0 to infinity of wk. Sorry, I'm missing the wk here. So the symbol sum k equals 0 to infinity of wk always means a sequence that may or may not converge, as sequences are wont to do. And in the event that the sequence of partial sums converges, the symbol sum k equals 0 to infinity of wk means the limit of that sequence. So in that spirit, the expression on the previous slide for a trig series refers both to the sequence of partial sums, Sn of x is a0 over 2, plus the sum from k equals 1 to only n now of ak cosine of k pi x over p plus bk sine of k pi x over p. And it also refers to the limit of the sequence if s of x equals the limit as n goes to infinity of Sn of x, if this limit actually exists. So a new complication from those series with the w terms on the previous slide, our trig series is x dependent. Maybe it will converge for some inputs x, but not others. This is rather similar to power series from calculus. We talked a little about power series in the notes last week as motivation for expressing a function not as a polynomial, but as an infinite series of polynomials. And we know from calculus that sometimes power series converge for a given x and sometimes they don't. And we'll review power series in much greater detail in complex analysis later. But the same thing could happen here with a trig series. Maybe it converges for some values of x, but not others. And we have another feature of trig series. We know that the nth partial sum Sn of x could be written in the complex form sum k equals minus n to n of ck times e to the k pi x over p. You can cook up what those coefficients ck have to be. So this suggests that if our trig series converges, we can write the full series a0 over 2 plus sum k equals 1 to infinity ak cosine of k pi x over p plus bk sine of k pi x over p as equal to the limit as n goes to infinity of Sn of x, because that's just what convergence of the series means, limit of its partial sums exists. But from this other expression for Sn, This is the limit as n goes to infinity of the sum from k equals minus n to n of ck times e to the ik pi x over p. So maybe this suggests to us that we should define the new symbol, sum k equals minus infinity to infinity of ck e to the k pi x over p, to be equal to the limit as n goes to infinity of the sum from k equals minus n to n of ck e to the ik pi x over p. This symbol, the sum from k equals minus infinity to infinity, is something I think that is new for all of us, that we didn't really have in calculus, where series just started at 1 or 0 or whatever and went up to infinity. So let's explore this doubly infinite case a little further. Suppose now that wk is a doubly infinite sequence indexed by the integer z. That is, we have a mapping from the integer z into the complex number c that sends an integer k into a term wk. How should we define the symbol sum from k equals minus infinity to infinity of wk? Well, the trig series work above suggests that we put sum k equals minus infinity to infinity of wk to be the limit as n goes to infinity of the sum from k equals minus n to n of wk. So this is sort of a symmetric sum. I'm starting at minus n, I'm stopping at positive n, I'm taking n going to infinity. So I'm sort of increasing the upper and lower limits of my finite sum here at the same rate. And we're going to call this synchronous convergence for a doubly infinite or doubly indexed series. And later on, much later when we talk about Laurent series in complex analysis, we'll see another kind of convergence of these doubly infinite series. And all of this has some non-trivial resemblance to the improper Riemann integral over the whole real line. And I talk about this more in the notes, and we'll point you to some reading in the appendices. You don't have to worry about that quite yet, but eventually we will get back into improper Riemann integrals with the Fourier transform, and you'll see the connections there. So let's talk now about the goal of all our Fourier series work now that we have the language of trig polynomials. The goal of Fourier series is to write a function f from the interval minus p to p into the complex numbers as f of x equals a0 over 2 plus the sum from k equals 1 to infinity of ak cosine of k pi x over p plus bk sine of k pi x over p, which could also be of the form sum k equals minus infinity to infinity of ck e to the ik pi x over p. And what should the coefficients be for f here? How can I define these ak's, bk's, and ck's? Well, if I started out with these equalities above, if I managed to write f as a trig series, and if I know I can interchange the sum from k equals 1 to infinity and the integral from minus p to p, or the sum from k equals minus infinity to infinity and the integral from minus p to p, then the only thing I could do, the only way to write these coefficients would be to have ak equals 1 over p integral minus p to p f of x cosine of k pi x over p, bk equals 1 over p integral minus p to p f of x sine of k pi x over p, and ck equals 1 over 2p integral minus p to p f of x e to the minus I k pi x over p. So proceeding formally from starting with these trig series for f and being able to interchange integral and sum, I get an idea of what these coefficients should be. And of course, this is exactly the same as what would happen if the series were finite and I had genuine trig polynomials. So what we'll do is we will define our Fourier coefficients as these ak, bk, and ck numbers, and then we will get a lot of mileage out of those definitions. We'll show that those were the right definitions for expanding f as a trig series, and we'll prove and calculate lots of interesting things about f with those coefficients taken for granted. So we call these the real Fourier coefficients, ak and bk, and the complex Fourier coefficients, the ck. And again, depending on what f is, since we're allowing f to be complex valued, ak and bk don't have to be purely real, ck doesn't have to have an imaginary part. When I talk about real and complex Fourier coefficients, I'm always talking about what am I integrating f against? The real functions cosine and sine, or the complex exponential? So this is our definition of Fourier series, this is our definition of Fourier coefficients, and we will spend a lot of delightful time talking more about these concepts.